Weird. Right. Excuse me. Good morning. I will give the same warning I started to dive with yesterday. Forgive me if I talk a little quieter or not as much today because I am still, it's not quite as bad as yesterday, so I am getting better, but I do still have a bit of a throat action going on. Drinking lots of water, so you'll have to bear with me while I moment at some point or a couple of times. Restroom. What is up, Johnny? Nice to see you, my friend. All right, we got the chat sorted over here. I think we're good to go. So there we go. Yes, so welcome. Thanks to anyone who's watching. If you are new or catch this in the future and don't know, my name is Tim. I go by Foamy Guy on GitHub and Discord, and I usually stream around this time each week, 10 a.m. Central Time, US Central Time, working on stuff related to CircuitPython. If you don't know what CircuitPython is, you can learn more about it at the main website here, circuitpython.org. It is basically a version of Python that runs on tiny computers called microcontrollers. You can plug them into your computer. You can open up a Python code file in your text editor of choice. You can write some Python code into there, and then when you save it, the tiny computers, the actual microcontrollers, and the chips that are on these devices will execute the Python code for you. This is just one of the ways that you can program microcontrollers. There are lots of others, but it is the one that I tend to work on here on the stream. CircuitPython is an open source project. Anyone's allowed to use it. Anyone's allowed to put it on their own microcontrollers. You can sell a product that supports CircuitPython. You don't have to pay for a license or anything like that. It's open source software. You can clone it. You can change it. You can do what you want with it. It is made possible by this company, Adafruit. They pay a team of folks who work on that project, including myself. They publish all the code as open source, even though they're paying us to work on it, which is amazing. If you would like to help support them and all of the open source software that they support, including CircuitPython, one of the easiest ways to do it is by purchasing hardware from them at their website, adafruit.com. You can get microcontrollers as well as all sorts of other bits and bobs that you can hook up to your microcontroller to make all sorts of fabulous projects with. So I am diving right in today. We are kind of sort of picking up on the same theme of what I was working on last night on the deep dive, but we are going to take a bit of a detour here, and we are going to try to learn how to use the Saleae logic analyzer. What is up, Gordy G? Greetings and salutations from Toronto. Nice to see you, my friend. Hope you're having a good day over there. And a logic analyzer is going to help with the stuff that we were working on yesterday on the deep dive, writing drivers for I2C and SPI. There are lots of other things it can do, but in my case, that's what I'm most interested in. And I will freely admit I'm brand new to this, so this is going to be me sort of poking around a bit, trying to figure it out, get it set up, get it worked out, how to actually use it on my computer and such. So if that kind of thing is interesting to you, then this work out for you. So my understanding is basically, I'll give you, I'm just going to kind of dive right in, but I'll start with what I kind of, how I imagine this is going to go. So on this device here, it's got these banks of 8 pins. It's like a Saleae version 8 or whatever. And so the 8, I think, is referencing these banks of pins here. I'm assuming that these are like input and output, or, you know, vice versa. And that essentially we just need to put this thing in between the wires we want to watch. There are some labels here, but they're not going to focus super well, and they are tiny. Okay. Interesting. Okay, so I was not quite right. These labels indicate 0 through 3 right here on the left, and I know you can't see this because it's not focused, but you can believe me for now. So 0 through 3 here on the left, top row. 4, 5, 6, 7 on the top row here on the right, and the bottom rows are actually all labeled G. Every single bottom row pin there is labeled G. I'm assuming that that is ground, but we will see once we get into it. My assumption is essentially we kind of have a sort of input-output type thing here. So I'll start with an I2C driver. We were doing SPI yesterday, so there's lots of wires here. I2C is only 4 wires, and only 2 of them are data, and really only one of them is data, one of them is clock. So I figured that's going to be an easier place to start than SPI, where we have a whole sort of mess of wires here. I'm assuming what we will do is essentially take SDA SEL from the microcontroller, run it into the Saleae instead of into the breakout, and then run it back out of the Saleae into the breakout, so that this will sit in the middle between the microcontroller and whatever component we're working on. And then there will be software, which we are about to set up based on what is in here, that will essentially let us capture the data that transfers through that Saleae. So we'll be able to watch and see what is happening on the SDA and the SCL ends. So there's a quick start thing here, which basically just says to go to the Saleae.com/downloads. It's got a picture of wire harness. It's got a picture of USB cable. Not the USB cable that's actually on the device, which is fascinating, but I don't even know. That's like it's another one you can't, maybe not, can't see it very well, but it's like, it's not doesn't look like standard USB. Anyway, let's not get on the doesn't matter rabbit hole here. I would also assume ground. Nice. Okay. So Saleae.com/downloads right there. Spell it right. Debug happy. Download for Linux. I'm on 2404. I think 2004 is very close to end of life, if not already. But hopefully this will just work. So it is an app image, which on Linux, app image is like a full self-contained, I don't know if binary is the right term for it. I think of it that way. The download that didn't really help me. Logic, okay. So it's like a fully contained thing. You can just run it. We probably need to make it executable, I'm guessing, actually. Yeah, it's not executable right there. It's only read-write, so I think we need to this one. And usually you can just leave it like that and it will thing. This time it did not. It said the set UID sandbox not running as root, common causes, unprivileged process using ptrace like a debugger, apparent process set pcontrol, failed to the new namespace, trace breakpoint trap. Mount logic, download. So presumably that's gonna mean you need to run it as sudo, guessing. Maybe let's... Logic 2 is provided an app image, contains all the files it needs to run. In Linux, you may need to allow executing. That's what we did with chmod to do this. Saying that stuff, that's fine. We basically did the same right there. Once it's allowed, simply double click it or run it, which is what I did. Oh, okay, no sandbox. That's kind of similar to what our error says. Yep, 20. So that's what I have. You may need to run it with that. Otherwise, it may fail to launch. Okay, fair enough. Can we tab it? Nope. Recording enabled. Welcome to Logic 2. Kind of dig dark usually. We take privacy seriously. We collect only information to help us improve stability in your product and your experience. This data does not contain information that personally identifies you or any data that you record. You can adjust the settings at any time. Crash report. udev rules allow non-root access. For data, please first install the rules file that is provided with the app. Instructions: while Logic 2 is running, open a terminal, run this command. Ooh. Really want to log out and back in. So it's gonna do what now? So it's imp has a logic.rules file, and it's gonna stick that into better udev rule. I'm gonna run that sudo. Oh. Disconnect. Would closing this and reopening it same thing? Should log out. Sandbox. Okay. Let's see. Hopefully we can get by without. Or not to do that, I have no idea. I assume that is gonna completely wreck the stream. I'm not considered that. Let's see here. It does come with a cable. We will. Here we don't need to be able to see, but mostly everything we're doing here is kind of small. This is the cable. The actual cable it comes with is just standard micro. Looks like USB micro cable. Got a standard looking micro plug on the back there. Very curly cable. Then this circle for a long time. Oh, there we go. Light turned on. I was gonna say it's plugged in, and it didn't really. Like, so I was thinking that was a light there, and it didn't do anything at first, but eventually. Okay. Yeah, this changed itself to see, like, clearly this has found the device is in a different screen than I left it, so I think we're probably okay without the logout, hopefully. Set up your capture. Configure this by selecting channels, sample rates, capture mode, and more. These settings will be stored for your next captures. Okay, and then that must have been, yeah, that was the top one here. Okay. Oh, interesting. I don't know. I just have the one at this point, so I don't know. Are there different ones maybe have different capabilities, I guess? Add measurements. I don't really know what that means all the way. Timing markers, okay. There should be a previous here, maybe. To areas of interest. Markers, I guess maybe that let you see how long a pin was high or low. You're debugging level analyzers and measurements. You can create your own Python extensions. Have my attention. Add notes, including notes. Capture. Straightforward. So we do 8 pins. See if the website got anything else about like using it. I think we got it installed. I don't think I need this. This. I don't recall ever seeing that term or anything on my computer. I don't recall ever having to do that with installing anything or seeing that come up before, so I don't know. I do have 2404. I don't know why, but it seems like I've had to do that before. Okay, so there is one with 16 as well. Okay, in the box. Input high at 1.2 volts seems very low. Over voltage protects safety minus 25 volts. Recommended I/O standards 5, 3.3, 0.5, and 1/8. So 3.3 and 5 are basically the two that we typically see on like CircuitPython microcontrollers. I don't quite get how to reconcile this with this, but it seems okay for the most part. Oh. Hmm. Okay. We'll keep that in mind. Software glitch filter might be important. Applies to all the input channels. Okay, so we have to set the voltage in the software, which is interesting. Except I don't see that. I only have... So they have voltage next to speed, but I only have speed and it's full width. Oh, there's the glitch filter. Okay. Huh. do that yet. We're gonna head there eventually. I2C is where we're headed. I don't see any voltage. I'm on sessions device 1. Open this thing. Detection test. Oops. I think we're detecting it. I'm just exploring a little bit, see if we find the voltage thing anywhere. Yeah, okay, we totally found the device because it's got this stuff. Capture setting. I have device settings instead of capture settings. So maybe you only started going. Stop. Can I delete that? How do we? Keep it too. Oh, maybe clear? Well, that's just gonna clear this. Or no. And delete data before. Mouse wheel does that. That's I don't want to get hung up too long on the voltage, but I also don't want to like break it or anything. I mean, I assume it's safe to be putting a microcontroller there, but odd that it shows you to pick this here and it's just not there. Hey, this looks like they're on a different one or the green thing there. I wonder, that must have been version in this. Search like 436. Got 4. Something like separate function for analog. So we're not actually analog either. Was in this. That's talking about voltage. Working with digital signals, the voltage threshold setting is still available, but it's located in different places. You can find it in digital voltage settings in the device settings panel, accessible from the right hand. Sometimes listed alongside the sample rate. By sometimes. I have no idea which one this is trying to link me to. Just keeps changing that back and forth. Why is this a link that doesn't So we're definitely in the device settings panel. Access it from the right side. It's the input voltage threshold. Okay, it looks like this setting is actually maybe just for the view that you get. Okay, because yeah, we have 5 volts. So we have 0 to 5 volts here. And I can control mouse wheel to zoom. And it changes. Okay. Yeah, I kind of think maybe that was... It's not actually setting maybe like the voltage you're allowed to use, but it might just be the scale of the output. This is all different, which is nice. We have more than 4 things here. Our play button is up here. Trying to do our best here. Connection status. Bottom now, it looks like, I guess. Capture settings panel. Used to be called capture settings, now it's device settings. Okay, and we have 2 channels. So I think these are enabled? Yeah, okay, I can enable and disable. So those 2 were highlighted because they're enabled. And okay, wow, we're getting a lot of a lot of pop-ups when I do that. Fair enough. Okay, so we could turn those on and off. Adding and renaming sessions. Click the plus to make a new session. Manage multiple captures. Okay, so we have tabs at the bottom. That's pretty sweet. Start button. Begin a capture. If it's not connected, okay, ours is connected though, so we don't care. And this will begin capturing data. You can stop it before it finishes. When does it finish? I don't know how it would decide to finish without you stopping. Excuse me. Time scale adjustment. Bottom right, maybe? Yeah, 88 milliseconds, mine says. Where am I? Order resize, connecting the... We already got it connected to the computer. Alright, it did come with these. Gen 2, 2x4 harness. Connecting the wires. If you have logic 8, 4 blacks are ground, they should be on the bottom. The 4 colored are signals, they should be on the top. Testbed colors match the channels in software. Colors reflect resistor color codes. Connecting ground. The 2x4 harness has a ground for each channel when signal integrity is a concern. High-speed digital. Connect to ground for each channel. Connecting noisy digital inputs. Noisy digital inputs to leads as far as possible from sensitive analog. Only one is needed when signal integrity is not crucial. We'll start that way. I suspect we'll probably be fine with just the baseline, but we'll see. The rest of them can be done floating, okay. Test clips. There was a bunch of those in the container as well. In the little case thing that it has. It has overvoltage. What's up, C. Grover, by the way, as well. I had accidentally rearranged my windows and had the chat hidden for a minute. Has overvoltage protection regardless of the setting. Okay, nice. And one, so we don't have this. Okay, let's get those plugged in. I really only need one right now, I think. And I will pick the correct one since they are color coded like it said, so we do want black, brown, red, orange. Yeah. A little dicey to have black as one of the logic colors. We want to go to 0, 1, 2, 3. Rounds on the bottom. Nice satisfying little kind of chunk there. And so wire 1 here is the... So it is, helpfully, it is the one black wire which has a white end thing on. Oh, okay, these are little shrink tubed, have numbers as well. So this actually has a tiny 0 on it. It's not in focus really, so it's hard to see, but... Slightly. I think I moved the camera. May still not be enough to see. You can kind of see the 0 there. Okay, so let's just go this for now. We want to go I2C. I'm actually just gonna unplug power and ground. Unhook these SPI datas on. Focus on I2C. And yes, I brought some of these because I thought this might be useful. I could go stemma to here. And so we want to go round for sure. I've got one of the bottom row black wires. It happens to be the one that's underneath number 0. But like the thing said, they're all internally, so I don't know that it matters really. I will... The voltage, I guess we would skip, right? Red wire, we don't really need... Red wire, we don't really need to go through the Saleae. So I'll do 0 as SCL, which I think is yellow. And if I'm wrong about that, then... And then I'll do 1, which is brown here, as SDA. And then this one, we will just connect straight through, I think. Wait a minute. No, I have done this wrong. So there's not an input and an output. Earlier I was saying about input and output from this, and that is just not the case actually. So we actually need to split off of this, don't we? We need to be, because I still need to get these to the breakout. Hmm. Looks like this. Yeah. We need like a T off basically. We need to go, we need SDA and SCL to be connected, microcontroller to breakout, and then we are going to be sort of patching onto the side of that. Like a wiring. Oh, through a breadboard. That's a smart way to do it. Okay. Okay. So we're on the right track here. This person's doing I2C as well. They are also using 0 and 1, black and brown. They also have one ground thing going to their microcontroller. And it looks like it's a little tough to tell, but I think whatever microcontroller they're using, there's actually 2 rows of pins here. And I'm kind of thinking it seems like maybe they're able to have yellow and blue coming off of there, as well as having brown and black from the Saleae 0 and 1 connected. Kind of what it looks like to me. But I think we can just do something like this. We can connect our breakout through a breadboard, and then we can easily just connect wires across those connections. Do this different. Unplug these. Why that would reset. Good. Skip a row in between. We'll do black and yellow. Oop. Oh, wasn't I? That's coming from this. So this wire is going to there. Then what I'll do is I'll take another one of these stem of breakouts, pair up all the same wires. I'll put them. My Saleae can be on the end. Theoretically, we should be able to just connect something here and have it work. Let's just check that. Inside my code.py file. Tabs, I mean giant commented out sections of an entirely different file. I don't think it actually matters on this device. Okay. All right. Okay. So we do have a good connection here. We're able to get data connection between the microcontroller and the sensor. So now what we would do then is just connect ground 0 and 1 onto those. Back a yellow. All right, there are literally no blue ones in here. Green instead of. I'll use the ground that's directly underneath in 0. I'll do yellow as number 0. Which is they're not quite input and output how I was imagining it before, but instead sort of just tapping onto the side of a. Theoretically now you should be able to like start a capture and see that stuff. I think what I'm gonna do is stop this and actually undo the loop so that we're just initializing. Inside of a init, there's going to be a bunch of, it sets a bunch of configuration things. It checks the chip ID. It does a couple. So there should be some stuff for us to see. No breadboard needed. Lower signal noise if a breadboard isn't involved. How can I would need a splitter essentially, right? Like in order to do it without a breadboard, I need an easy way to kind of tap on to the side of a connection. So I think I would need like a wire that's kind of a splitter, essentially, like a 1 to 2 type thing. Because then I could go one side to the breakout, one side to the Saleae. And and that would be on the 2 side, and then the 1 side it would go to the microcontroller. Or is that what these little? So it did come with these. It is software use. Camera's not up. It did come with these, which are connectors in some capacity. Okay, so this has a little sort of grabby bit. Okay. Let's try this one since we're set up for it. Use the breakout second. Oh, okay, we could use the pins on the breakout. Good point. Let's try this since we are wired for it and we're ready to hit go. But I will try taking the breadboard out in a second as well. Nicely. All right, so we have channel 0, 1. I have no idea what speed would be appropriate, so I'll just leave it on what it was set to. Start this. Right, stop that. Saw it go by there. Okay, hold on. That is zooming. How do I go sideways? Possible to go sideways with the mouse wheel? Alt scroll does nothing. Control scroll changes these voltages. Shift scroll does nothing. Shift actually is turning this thing on. Dragging really the only way to scroll sideways? Wait, wasn't regular? That's zooming. Like dragging is the only way, but we can zoom super far out. So, and in this case, 0 is SCL. So 0 should basically just be clocking kind of back and forth. And then SDA would be the actual data here. Okay, so we did capture it. It looks a little well, okay, we have our square up here. Okay, this one is, oh, okay, analog, so that says A0, A1, and then D0, D1. Okay, I see. So digital, I'm most interested. Have a that behave, but okay. The control scheme, I'm not quite. I really want to mouse scroll to move side to side. It's gonna take me a minute to get used to thing. So there's our very clean up down up down up down clock, and then here is our actual data. And presumably somehow here we could pull out actual data from this. But yeah, let's take the breadboard out of it. Having analog asking with the digital signal is very useful. Cool. Yeah, it is interesting. It shows you both. I didn't realize. I thought it was going to be like a set one or the other, and it kind of just shows you the one. But yeah, being able to see both is cool because you could tell if you're like maybe you're not getting quite high enough or something, and it's not registering as a digital peak. It just would not show anything here, but you'd be able to kind of see that here. Okay, so let's clear this. We have gotten a capture successfully, which is pretty sweet. Clear this. And let me try to rewire it a little bit. So let's get the breadboard out. Going to hook logic pins and then ground from the Saleae. Plug these. So what we could do, I think, so we could use the ones on the breakout. Another thing I could try. I also have one of these stemma female jumper ones. I wonder if we did this. Select. I leave a gap or just it'll pull up. Sensor plugged in. Oh, I also don't have into the sensor. Okay. Okay. So now I have breakout to female, male to male, stemma to. I can't. in here. 1 second. Being weird. I'll be right back. Okay. And then I think the way this works is these things plug down into there, basically. I am going to go back to the picture we found. Take a Yeah, you can't really tell from this picture. They're on the bottom side, but there's kind of like there's a hole there, and it looks like there's a little pin inside there, which I'm assuming the female wires from this thing can connect to. I've got this thing grabbing onto ground. Go ahead and connect this ground to it. Two more of these. Actually, hopefully there is kind of a gap there. Little grabber is like a sort of a little pinchy lobster claw like thing. It's got two arms or whatever, and they can kind of grab onto this and they spread apart when you down. All right, so we'll do the same. 0 to L yellow. One, which have like a little sort of tactile click when they plug in. I'm not sure if I got them all connected correctly. Use regular stemma to stem to the breakout and then connect that to the second breakout connector. Yeah, I will do that as well here in a second. I'm just kind of curious about if this way works too. Because like at some point I might be in a situation where I have no pins that are like there might not be a second one on there in some situations, right? The male pins on the breakout might be easier. Yeah. I think so as well. Let me I'm just kind of see what works. Yeah, at this point basically I'm like okay, so I think is connected. Like I said before, some of them had like a bit of a more tactile click though, so I'm not sure. Oh. Okay, yeah, we still got everything. Like we're connected well. Okay. Yeah, let me delete that and then I will do it that way. Change it back. I'll change it over to use the pins. Select one more time after this. Also, what's up, Tyth? Nice to use here. I'll put back plugin stuff. grabby claws back in their little. I don't know if there's a couple floating in there. Like this one does. Has 8 holes to grabby claw. Other one in there that has 8. I don't know if it was supposed to come with 8 or one's only supposed to have 6. Okay, so instead we can do what they said. So we'll unplug this. Spy wouldn't have. Yeah, on Spy we would basically would have to use. Well, okay. I mean, it's not technically a breadboard, but I suppose I could use the doubler here, right? It doesn't matter where I connect. Like in my head's model, it makes sense to connect in the middle, but electricity doesn't really work that way, does it? I don't think so. I could maybe just connect 2 fire I2C pins on this breakout. Now, on boards where stemma is not the same as the pins, like there are some that are like that. I don't think this is one of them. But in that situation, then you wouldn't be able to do I2C very well. Spy you could still do, though, because mostly Miso, these are all broken out over here. We could connect to them. So that is something to test, actually. That would make it super easy to be able to just connect onto that as well. Okay, let's try this way with the breakout pins. So I mean, as you can tell, I'm very much in discovery mode at this point. Let's just kind of throw stuff at the wall, see what works, what doesn't. So I will say this is a lot of wires. It's not helping my desk of trouble. Okay, so we could then connect to these pins. So on the breakout, there is so VIN 3 volts out and then ground. Go and snag the ground that's underneath 0. And this, I'm gonna look at the guide. Well, is this one labeled? Okay, they are labeled. I'm used to I've been looking at the SPA 06003 the last couple of days. That one, on the silk screen, it has like SDI and SDO stuff, so it's like quite labeled the same as I'm used to. Okay, so ground is in 0. We'll do SCL again. Next to it. And then 1. Brown. Am I gonna like learn resistor colors through osmosis? So there is one in between, so we're gonna skip one and then SDA is. And then let's see if that works the same. Boom, yep. Looking basically the same as before. Okay, so can we get like, how do we get the data out of the electrode? Because at some point we're gonna want to look at that any spike there. What is that measure? Lets me leave a comment there. Has a maximum, minimum of some things that I don't understand. Look like speeds. Number of falling edges for delta T. I guess how much time it is. Find more measurements. All right, so basically this is just letting us like notate stuff. Analyzer. Oh, I2C? Okay. Channel SDA is 1, SCL is 0. Show in protocol results table, stream to terminal. Sure. Ooh, there we go. Now we have some extra stuff here. So setup right, 0x47, we got an ACK. And so this would be in the, I'm just going to kind of follow along in the code here, so make sure my own head is wrapped around this properly. This would be the chip ID first, I think. So inside of init, the very first thing this does is set up I2C device and SPI device. Call reset. Oh, okay, actually command is the first thing. So command is at register 7E. 47. I don't know if this worked right, because we kind of always have 47, 28, 47. Set up to read 47. You can click on this, but it doesn't really do anything. Control click to scroll table row? Scroll table row. Okay, it scrolled me to that. Okay, here we go. So there's 7E. That's what we did there. So 47, that's the I2C. That's the device address. Yeah. Okay. That is the device address. And on I2C, so my head is in SPI mode because I've been working on SPI driver lately. And in SPI, obviously the chip select is how the peripheral knows that you're talking to it. In I2C, there is no chip select, so I never really thought about it, but presumably it must be sending the device address first. So every device on the bus receives actually every transmission, but it always just reads the address that comes first, and if it's not its own address, then it must ignore it. Okay. Interesting. That's pretty cool. Okay. So that's just kind of establishing communication with that particular device. And then we do have 7E here. Can I go the other way? Can I control click this to get... No. Okay. Oh, maybe that, actually. There it is. Okay. So how far is this in? That's in the middle one. All right, yeah, there's our 7E. Okay, so we're writing to 47. We are writing to register. Now, that's device address, and then that's register address. The data that we wrote was what? So that was the reset command. Sea level pressure, which was there if you happen to see it, is not a register. Doesn't actually do anything on the bus. It's just a number. And is B6. All right, so B6 is actually all the way down here. But that's because when we do a write, by default, we actually do a read first. In this case, we're writing an entire byte. I'm pretty sure the command register is a whole byte. Yeah, I think that's right. On this device, I think that's right. But in some cases, you might be writing less than a full byte. And in the case where you're writing less than a full byte, what you want to do is, and what the code does inside Adafruit register, it will read from the register first so that we get the data out of the device. Then it will shift the new value you want into the correct bits. So let's say if you were only writing 3 bits or something, you would read a full byte, you would put your 3 bits into that byte, and then you would write that modified full byte back. So this is reading the register 7E, the command register. In this case, we actually just get back 0 because the command register always reads as zeros if memory serves. Then we plug in the values that we actually want to write. In this case, it's B6. It's a whole byte, like I was saying, so this whole thing is kind of moot in a way, but that's just how it works. We are then writing that B6 back to register 7E. So that is the reset command getting written. That is right there. That is actually, okay, that is the last of this first little burst. We had kind of 4 chunks here. And the last one of those is that reset command. And then next, what do we do after that? I2C is just a bus, yeah. What is up, Tithe? 100% use the doubler. Sometimes being in the path is better, but often any point of nearly equivalent level is fine. Okay. We are, I think it's going to be inside of here still. So the next thing it does is it tries to read the chip ID. And this device in the datasheet, it actually said something like this. It said you should try to read the chip ID once, just like and throw it away, essentially. If I recall right, I think that doing this transaction and ignoring the result is helping to set it correctly into I2C or spy mode, basically. Like when you do this, it's determining the determining which one you're actually using. And you get a bogus value, so you just throw it away, but then afterwards you can pull it again and get the correct value. So chip ID, that is register 01, which indeed right here we're going to be doing basically the same thing, right? So we would read from register 01. Looks like we got back a 50. So actually it looks like in this case we did get a real value because I think 50 is correct. But this one would have been us getting it and throwing it away. Right here. That one. And then the next one here would have been right here, getting it and actually keeping it. After that, in the code, we validate the chip ID, but that doesn't do anything on the bus. Next up, we do check the status NVM ready. And this is 28. Here we have 28. And it's the same, actually, status NVM ready and status NVM error. Those are the same register. Yeah, so those are both register 28. But they're different bits inside of it. So here we're reading NVM ready, and then here we're reading NVM error. They just happen to come from the same register. Go here. Got back 0x02. But we can't necessarily... Oh, there we go. Nice. Okay, so we can change those. So yeah, and this is kind of cool because if we have this in binary, then we could be looking at register here. So NVM ready. This was 28 status register. So now we have this binary right here in this table, which I cannot highlight very well, is matching up to this value we just read right here. So it's, in this case, it's all zeros except for this one here, index number 1, which matches exactly what we got. Those are reset values, so that's what we expect. We just did a reset. These are truncated, so we can't see it there, but if we go look right here, we can see index number 1 is the status ready bit. So status ready bit is 1. The NVM error is bit offset 2 right there. And of course, we know in ours that's 0, so we had no error. Sweet. A little wider, but I will go back to hex for most of the time. I think probably hex is generally easier, right? Because you can see the addresses and stuff. Okay, so this is pretty cool. I think we've got this sort of pretty well understood. I'm getting the idea here. And that is, we are now in the second burst, basically, of X. Okay. The next thing that we can see here is this going after register 27. Presumably that is this interrupt status power on reset delete bit. So that is bit number 4 inside of register number 27. 27 here. It's 10. That being able to go there and then there we go. So bit index 4. So 0, 1, 2, 3, 4. That bit is high. So that means that we have successfully completed the power on reset. Almost want a keyboard shortcut. Each. That would be cool if it was like B doesn't do anything either. H and B, it would be nice if it would flip those for you. Okay, 36 it goes next. I'll stop here pretty soon. I'm not going to go through the entire process because I do think I have this understood at this point, but we will keep tracing. Ooh, okay, that's a lot of resets. I don't think we need that many. I will chase it just a little bit further. So the next thing we got, temperature oversampling. Presumably that is going to be register 36. Indeed, OSR config register. So the oversampling rate, that's, okay, so here's a good example. This one is 3 bits. So in this case, this is where that reading the data out first, then updating it with the 3 bits that we want to change, and then writing back the modified full byte really comes into play here. So register 36, it looks like we did get a 0. I am just going to double check here. I presume that's just what we expect after a reset. 36, yeah, all zeros, middle row there after a reset. That tracks, and then we went and we wrote up to write to, like we wrote a 1 in this case. Temperature, I think I clicked the wrong one there. Temperature oversampling 2x, and indeed it is hex value 1. And then we are going to go and write the pressure oversampling rate, which is actually in the same register, but it's 3 different bits. So here is going to be us reading that register after we've just written the temperature oversampling. And it's now set to the value we wrote to it right there. So we've now got the data we read. We update that with the pressure oversampling, this here, 0x4, into the 3 bytes that are for that, which would be bits 3, 4, and 5. So those are updated into there, and then written back right here. Like we do more configuration. IR filter. Actually, 37 is going to be... Might be bit shift. No, bit shift enabled. That was a thing on the SPA, actually. We didn't have to do that on the BM. Yeah. That must be this. IR filter. Oh, that says 31. Could have written both oversampling rates at the same time. It's true. It would have been possible, like on the bus level, it would have been possible to write both sampling rates at the same time. The reason why it doesn't ultimately boils down to the fact the way these are created as descriptors. So like in the code here on the Python side, it's actually setting a property essentially. And there's no, like, when you set this property, you're actually setting off that whole chain of events to read the current value, slip in the bits that you want, and then write the updated result back. All of that happens just by you doing this on the Python code. And there's no mechanism to tell it to, like, wait or not commit the write or something like that. If you were just using the bus, if you were not using these RW bits, these things here, you totally could, just with your bus, like, read the full byte, update everything inside of it that you care about. In this case, you know, both oversampling rates are in the same byte. You could write both of those at once, or modify both of those at once, and then write it back in and save yourself a whole cycle of reading and writing. Yeah. But it's effectively, it's like a trade-off. This part makes the code sort of easier to use and easier to write and easier to understand. But the trade-off is, in this case, yeah, we totally are making extra transactions. So 37 is weird. I'm not sure why we get... So after we wrote the pressure oversample... Oh, output data rate. Okay, I just missed this one. Pressure, that must be... Output data rate, this must be 37. Yeah, okay. Yeah. And we are setting that to 50 hertz, which is... I wish these would show... Sometimes these show me the number. This little pop-up will actually have the value, but I think maybe const is throwing it off. 0f value. Right. So yeah. So we read... So we read from it. We got 70. We would have then slipped in the 0f, and that ultimately gave us 3c, which we wrote back. And then we're actually back on 236 again. So we could do whatever this one is doing. A pressure enabled is actually in that same register as these as well. So theoretically, these two top ones and this bottom one could have all been one transaction. Okay. And then these are going to be essentially the same, I think. Different registers, perhaps, but effectively kind of doing all the same stuff. Okay. I think that I have a pretty good grasp, at least on the basics of how this works, how to, like, get useful information from the screen here. The scrolling is still throwing me off, but if I use it enough, I'll get there eventually. I do like this. This is kind of nice how you can kind of go through. So you almost have two views here. You have a table of raw data, and then you've got the timeline of up and down. I do like the way this lets you essentially sort of just scroll through it by clicking on all these. Okay. Sweet. And then this is the last exchange of the 4. I think I said 4 the first time because I was looking at that as 2. Okay. Okay. That is pretty sweet. So I think what I will do is start looking back at what I was working on yesterday on the deep dive, which was SPI support for the SPA 0603 driver. And where I left this yesterday on the deep dive was we were getting zeros for temperature and pressure. And I actually realized after the stream that the code we were looking at in here I wrote this stuff afterwards, basically. This logic is still wrong. And I also had the epiphany at some point last night, right before bed, in fact. I was way overcomplicating this. So first of all, I have just arbitrarily chosen 4, which I don't think was correct. This should be address length, which we will have as self.address width. Actually, I called it width, not length. So that should not just be 4. That's wrong. And then the other epiphany I had is we are converting this number to bytes right here. And then last night I was trying to convert it back to a number and then bit shift bits out of that number into a byte array. But that's like 2 steps that just do not need to happen. We have the bytes right here. I should be able to just take those bytes and put them in the buffer. So I think this all was not really necessary. We could just get, well, so let's fix this. Self.address doesn't want to show up because technically this is like a super class, and then the subclasses have that. I don't know. I'm not sure if there's a way if I did like sure if that's filling in because I did that or because I had written it before now, but I don't know what this, I'm not sure if this will break it either. Okay. Yeah, probably the 4 there. So frankly, the math here might have been right. I'm not sure whether or not the math here was right or not, but it actually might have been right. And having the hard-coded 4 here could have been, I think, maybe what broke the ability to actually read real stuff. Nicely done. Yeah, thank you. I mean, I will say, like, they've got it pretty well. I like this. I like the way that this is all set up, and it didn't, I mean, knock on wood, I didn't have any, it was not a big fight to get it recognized and get stuff plugged in, so I definitely appreciate the fact that it was more or less plug and play. It's like a very specific tool, you kind of know how to, you have to know how to play with it to get anything useful out of it. But we didn't have to fight it too much, which was nice. Another thing we could maybe do is just reverse the bytes. Well, so I mean, I think this would reverse them actually. If this was a gardening channel, you'd speed it up by 4x and create a short. Yeah, there you go. Yeah. So this would give us bytes, and we'll have as many. So we could do some. So I think now we could do something like this. So we could say for I in range address width, and then self dot buffer. No, it's just buffer. Actually, there's no self buffer. I. Are we reusing I? Hold on, we can't do that. Actually, I is here. I. Set that equal to that. So this will reverse the order of the bytes in the address, and then this will go and pack those reversed bytes into the buffer. And there is no need to go back to a number and then do any bit shifting, because buffer is a byte array already. And that's where we want to end up with the thing in address. Save that and then re-hook up the SPA. So I will plug 0 and 1, unplug ground. Bring this mess of wires back. I think better eat. Three volts are the two pins next to. I have yellow. Okay. We have starting from the end, we have D4, EX, RX. Then it's Somosi, and then it is SCK. Should have Miso Mosi, EXRX, and then yeah. This case, so this is the one where the labels are. So it has SCK is labeled normally as SCK, but then there's SDO and SDI for serial data out, serial data. Yes. Serial data out would be I'm gonna go to the learn guide. Since I'm guessing when I time to document. Okay, yeah. SDO goes to Miso. SDI goes to Mosi. Do these in the. I have orange on SDI. That is to SCK. E. O. That one is chip select. SPA 910. Yeah, I think that should be right. And one more. So here, I was cheating by doing this yesterday. I'm gonna undo that. Ultimately, we don't want to have to do that. Ultimately, it should handle it correctly for both LSB first and LSB not first. And it should not need to explicitly have another check for the address width. It should just have logic that works correctly for the address that we have. Okay. Let's run that. Okay, that is working now. That's good. Cool. So that means we're at least no longer breaking single byte addresses. Now we are successfully, in fact we know because the BMP is LSB first and the SPA is LSB not first. So we know both branches of these logic now are working correctly for single byte addresses. The thing we still don't know just yet would be multi-byte addresses, but I still don't know for sure of a device that's actually has that. This stuff I think is fine now. This. I think we don't need this to be a variable. Cool. Sweet. I think the 4, honestly, is what was wrecking us there on last night. The math of bit shifting might have actually been correct, even if unnecessary, since, as noted here, we want to end up on bytes anyway, so it's kind of superfluous to convert back to a number and then convert back to bytes again after that. But it might have actually been correct, and just the reason why it wasn't working is because we had this on 4. Because I think yesterday I was thinking in Python an int is 4 bytes, which may be true, but it's like irrelevant to this part of the code. I don't think that matters. We care how wide the address is, not necessarily how wide an integer in Python is. I just got hung up on that conversion last night. And the rest of this seems to be working. Let me run it again. Yeah, so now we're good. We've got SPI data coming out of the SPA. We're reading it successfully. We got initialized. Thing is all good. And I only have one of these, so I cannot easily do the double SPI test. The main reason you might want to use SPI over I2C would be if you wanted to have more than one of these, right? With I2C, you can't, because they would have the same address, although there is actually a jumper. You can change the address, so you could have 2 over I2C if you changed one of their addresses, but ignoring that for a moment. Here, you could just have 2 connected. You wouldn't have to do any address shenanigans, because they would have their own CS pin. But I only got one. The BMPs, I did successfully test with 2. I think I showed that last night. Okay. I think what I'll do here is submit what I have for the new version of the SPA driver, which is the one that supports both I2C and SPI. and I will update my PR in Adafruit register with the latest version of my code for that. And then I think I'll probably wrap it up after that. Why do I have changes? What are these? If I change this, we can keep that. Some I2C devices don't have jumpers. Yeah, for the address, yeah, some of them don't have the ability to do that. In which case, if they do support SPI, that's where you can, like, if you need more than one, SPI bus is your friend, because you can get as many as you have chip select pins. I don't know if that's, maybe there's a smaller limit at some point. Not sure if the SPI bus itself has any limitation, but you definitely get more than with I2C for sure. This is, oh right, because I just haven't updated this yet. Okay, so I will just do this. I will do this. I'll just leave this on 0.10, I think. Oh, I thought I copied. That's from the device. We'll paste that in the repo. So there should only be changes for, like, we added SPI device. We changed where we changed the RW bits and RO bits and all those. We got those from register bit and register bits instead of I2C specifically. We of course need the accessor, SPI, and I2C. We have typing now for digital I/O because we have a CS pin. I did change that to generic scripters. I found these. I found actually kind of a cool thing to write all of these. I was actually pretty proud of the way the documentation for this turned out. Let me show you the documentation real quick. I was able to use Cloud to write these tables though, and I thought it was actually a really helpful thing. Because a couple of these values, they only allow certain things, right? Like the oversampling or something, for instance. So I figured out how to get these tables in here. And when I say I figured it out, really what I mean is I figured out that what you can do is I just went up to the constants up here. I copied all of these, I dropped it into Cloud, and I asked it to make me an RST documentation table of those things. And then it spit out the RST text that I could paste into here. Which was super, super nifty, right? Like this would be a huge pain in the ass to hand code this table, right? Even like copy pasting and stuff. Like it's so intricate to get all the right stuff in the right places and everything. But it did it correctly the first time. I just gave it the constants, asked it to do that, and it was like, yeah, here you go. So that's actually really cool. I think I'm going to go back to the BMP driver now and do the same thing, because I didn't, in the BMP driver, I think the docs just say, like, you know, must set this to one of these constants or something. It doesn't actually list out the table anywhere. Yeah, IO expander as well. There are a couple, there are devices that will let you, they kind of work around the I2C limitation. They give you a splitter, so to speak. Okay, set up the device, and then everything else is the same. Yeah. The only real changes are being able to make a SPI device, and then, of course, using the accessor layer, and where we import that stuff from, and the name of the class. In this case, I changed as well. Everything else is, that's basically it. Branch by support. I will go ahead and do a SPI test as well. So this is the I2C test. 06003 SPI. A simple test. am missing the header. So that from one. Okay. Pre-commit. Oh, I'm in docs. Let's try to. Well, let me do pre-commit. Can I do pre-commit from in here? I'm gonna go out. I don't know. Actually, the docs are gonna fail because the classes that it uses in register are not published and also are not installed in my Python environment that I'm inside of. So Sphinx is gonna go try and find these classes, and you can tell PyCharm, in fact, is underlining them red also because it knows that they can't find them. Basically, they're not in the environment that I am inside of here. I could install it, like the register. I have the repo. It's just not installed in the virtual environment. I could do that, and then it would work locally for me. But it would still fail GitHub Actions too, though, because that's going to take the published register. Oh, I don't have a remote for that one. Work yet. You circle your mouse, it goes faster. Oh, I wish this. Oh, I don't know why that doesn't start focused in the top box. It's a little awkward to start focused in the bottom box, but I guess they just expect you to use origin. I don't really like to use origin. I think I picked that up from Scott. I like using the remote name. So Adafruit if it's an Adafruit repo, FoamyGuy if it's a FoamyGuy repo, so forth. Like a fork, I should say, not repo. And then this is pretty much the same as this one over here. So I'm just going to steal. We should check I2C, actually. Any reason why it wouldn't work, but I should double check that, especially since I'm about to put in the comment that I. Let me do that real fast. Here. Yeah. That one is connecting over right. That's both. That's working. make this as draft, because really the register, this needs to go first. Okay, and I will update that register PR as well. Take off for the. Ooh. Already have some updates here. I think I just pasted my state at the end of the stream last night. Knew it wasn't working quite yet. I think I just copied them into the repo. That way, like, if the flash on my device were to die or something, they'll have the work did. Okay. Oh, we should get rid of that. Interesting. We should run pre-commit. I think that's because I made this change here, but didn't actually save it. Need to explicitly save after that. Lines there. Well, oh, well, it wants a blank line before the function, actually. And I fixed that as well. Did I fix that for I2C? I think I did that yesterday. Need to be... Yeah, here we have start and end. That is address. We have... Oh, right. I had to add signed. I didn't have that before. I got rid of that. I don't think it was doing anything new to handle signed stuff. That's also handling signed. Okay. Good. And then bits. Well, bit, it looks like, did not actually change. So it is interesting because it was different a minute ago. Only formatting looks like. Probably what happened there is occasionally, like I can run in PyCharm, if you do Control-Alt-L in a file, it will format the code, but it doesn't use rough. It uses something. There's probably a way I could get it to use rough and get it to use our configuration. I haven't bothered to set it up. It does its own formatting though, and occasionally it disagrees with rough. So I probably had done Control-Alt-L, got it formatted by PyCharm, and then pasted that in. And since I just did pre-commit, now it formatted by rough and went back to whatever it wants it to be, which happens to be how it was in the repo before, because I also had ran pre-commit the last time I committed. All right, so basically here we have spy start and end fix. And big and also in bits we added sign and signed. All right. We are pushed up there. Sweet. And yeah, I linked SPA to here as well, so now that shows up. And then I can fix some of this. So I said this was wrong. All right. That is going to do it for today. Thank you, everyone, for watching. Hope that was interesting. I definitely learned a lot. I will be back. I should be back at the normal times next week. Interestingly, this is now just showing me as offline, which is odd. Oh, there it goes. Okay. I should be back at the normal times next week. So Friday for the deep dive on the 3rd of October at 5 p.m. Eastern, 2 p.m. Pacific, 4 p.m. Central. And then here on my stream on Twitch and YouTube on Saturday the 4th, 10 a.m. Central Time on Saturday. I'll be back for that. Until then, hope you all have a good rest of your Saturday. Have a good weekend. Have a good week. And I will see you later. Thanks for hanging out.